Let's look at another example of an inductive proof here. This says, state the explicit rule for the nth term of this recursively defined sequence, and then use mathematical induction to prove that this is in fact the rule. Okay, so let's first find the explicit rule here. The first thing I would probably do is write out the first few terms. So the first term we know is a 7. The second term is going to be, according to this recursive formula, the first term plus 4, which would be 7 plus 4, which would be 11. And the third term we can see would clearly then be, if we add 4 to the previous term, it'd be 15. So there are a couple ways you could get the explicit rule. Let's just look at, I'm going to look at this way here. We can write these in the table. So the first term we know is a 7. The second is an 11. The third is a 15. And if I go back 1, I would say that the 0th term would have to have been 7 minus 4, which is a 3. And I guess the reason I'm doing that is because we can use our knowledge of linear functions to see that this is a resembling a linear function which has a slope of 4 and a starting value or initial value of 3. So I can write this. All right. So now what we want to do is we're going to use mathematical induction to show that this explicit rule works for all natural numbers. Okay, so we'll start with the base case. So I'm just going to add base case is n equals 1. So does this statement hold for n equals 1? Well, the first term is a 7, and is that equal to our explicit rule, which would have it be 4 times 1 plus 3? Yes. Okay, so that's true. So it works for n equals to 1. Now let's show that if it's true for the kth natural number, that must mean it's true for the k plus first natural number. So we're going to assume that this is true for the kth natural number. So a sub k equals 3 plus 4k. So I didn't write out in words the words. We're assuming this is true for the kth natural number, but that's what this is saying here. And we want to show that the explicit rule would work for the next natural number, which would be 3 plus 4. Okay, so we're going to start with this. Now you want to take note of what it can get confusing in terms of what are we allowed to use. One thing we're allowed to use is we're allowed to use this basic recursive formula that we started with, right? That is the rule we're sort of grounding our whole understanding in here. So we can use that relationship. This whole proof is to show that this relationship for giving this sequence of numbers can be shown directly with this explicit formula. Okay, but we can surely show, or we can definitely just assume that this is true. And we can also assume that this is true. So those are the two things we're allowed to use. So the first thing I'm going to do is I'm going to use the recursive rule, and then we're going to probably use this in the inductive hypothesis here. So according to the recursive rule, if you were to just talk about this in words, the recursive rule would say that any term is the one before it plus 4. So for our k plus first term, that is the one before it plus 4. So we're allowed to use that. And now I'm going to use my inductive hypothesis. I'm going to replace this with that. And once we simplify, hopefully we get this. So this equals 3 plus 4k plus 4. And now you can see what's going to happen. Now I've just rearranged the terms and I've shown exactly what I want to show. Right? So if it's true for the kth number, that necessarily implies it's true for the k plus first number, and now our inductive proof is done. I'm going to give you one last inductive proof here, and only just so I can give you kind of a little sample of the types of situations in which it's useful. So this says, suppose that f sub 1 is 1, f2 is 1, f3 is 2, f4 is 3, and f5 is 5. And in general, any term is the one before it plus the one before that for n bigger than or equal to 3. So you may not notice, but these are generating the Fibonacci numbers here, okay, where you get the next term by just adding the two terms before it. We want to show that this identity happens to be true for the Fibonacci numbers. Now, there are a ton of interesting identities that go along with the Fibonacci numbers. This is just one of them, and inductive proofs are actually very useful to prove those. So I came across someone who had like a book that was just all these Fibonacci identities, and really you can understand them, directly, which takes probably a lot of thought and careful arrangements of things. But if you suspect something's true, you could probably prove it inductively and at least show that it's true, even if you don't quite understand why. Okay, so let's start. So the base case, now in this case, we got to keep in mind the base case is going to be that we need to show it's true for n equal to 3. Okay, so that this relationship here is true for n bigger than or equal to 3. So and the other thing is that the Fibonacci numbers really require that you have two initial conditions, right? You need the first two numbers to get the third. So for n equal to 3, let's see if this claim here is true. So is it true? Is it true that f of 1 or f1 plus f2 plus f3? Now, according to this claim up here in the box, that's supposed to be equal to, now look at the relationship here. This is the nth term. N plus 2 must be two terms after that. So that must be equal to, or the claim is that that's equal to f of 5 minus 1. So let's see. So I'm going to put a question mark here. Well, f sub 1 is 1, f sub 2 is 1, f sub 3 is a 2. Is that equal to the fifth Fibonacci number, which is a 5, minus 1? And yes, they're both equal. Both sides are equal to 4, so that is true. Okay, so now we go on to the inductive step. So we're going to assume that this is true. F sub 1 plus f sub 2 all the way down to the kth Fibonacci number. We're going to assume that's equal to the k plus second Fibonacci number minus 1. Okay, we want to show that would imply that this claim is true for the k plus first natural Fibonacci numbers, rather. So just again, the indices here, if this is a k and that's k plus 2, this must be k plus 3 minus 1, right? 2 more than it. Okay, so we're going to start with this expression, and we're going to show that that must equal what's on the right there. So f1 plus f2 plus f3 all the way down to the kth plus the k plus first. So I wrote the kth because we're going to substitute this first or most of this expression with what we can assume is true. By the way, notice I haven't really, this is the last thing I'm going to be writing down on the page, right? That is, we want to end there, at least the style in which I do these proofs. Okay, so we're going to end with that statement. We can't treat this as true. We have to show that that's true. But I can replace this, right? I'm going to immediately use my inductive hypothesis, which is that expression is equal to this. We're allowed to use that. So I'm going to replace that. So that's f sub k plus 2 minus 1 plus f sub k plus 1. Okay, so now it seems kind of hard to imagine how we can get us f sub k plus 3 out of this, because that's what we want to show here. But we want to, the other thing we can use is just the original recursive formula for the Fibonacci numbers, right? Any number is in the Fibonacci sequence is the one before it plus the one before that. And if you sort of look at what I have here, if I just rearrange this, I'm going to write these first two terms first. You can see that these, right? This is the structure of the Fibonacci sequence, right? I've got a number plus the one before it. So what number am I actually referring to? What number would I get if I took the k plus second term and added it to the k plus first? I would get the one after the k plus second, which is the k plus third. And so I make that substitution, and now my inductive hypothesis has gotten us to this point, and the proof is done. Why don't you go ahead and try to prove this claim using mathematical induction and see how it goes for you.